Assalamu alaikum. This video inshallah will be the continue of tutorial number 5. In this video we will solve about the actual Rankine cycle. In this question we have he said consider a 210 megawatt steam power plant. So this power means W dot net, okay, for the power plant. So we have the W dot net equal to 210 megawatt, okay, and usually we deal with kilojoule per second, so it is in kilowatt, 210 times 10 to the power 3 kilowatt. That operates on a simple ideal Rankine cycle. We will ignore this. It is there is a modification for question number 16, which is question number 1017, that assuming that we have an isentropic efficiency of 85% for both the turbine and the pump. So when the isentropic efficiency is mentioned in the question, that means that the question is about actual Rankine cycle, okay? So we will ignore this word, okay? And we have actual Rankine cycle with isentropic efficiency for pump and turbine. So for pump and turbine, the isentropic efficiency are equal, which is 0.85, okay, 85%. Steam enters the turbine at 10 megapascal and 500 degrees Celsius. Enter the turbine. Where is the inlet of the turbine? Inlet of the turbine is state number 3. If you start number 1 at the inlet of the pump, okay, it is state number 3. So what is given is state number 3, the pressure and temperature for state 3. Okay, here is the TS diagram for the actual Rankine cycle. Okay, in the ideal cycle we have isentropic compression and isentropic expansion, but here we don't have isentropic process. So we will go to the right and up in the compression process, and right and down in the expansion process. Okay, so that is the difference between the actual and ideal Rankine cycle in TS diagram. Okay, so we have B3 is equal to 10 megapascal, which is equal also in kilopascal 10 thousandths. Okay, kilopascal, and B3 is equal to B2, right, on the same pressure line. Okay, and we have T3 equal to 500 degrees Celsius, and is cooled in the condenser. So it is cooled from this temperature T3 until state 4 in the condenser. The condenser is from 4 to 1. At a pressure of 10 kilopascal. So the condenser pressure is P1 equal to P4 and is equal to 10 kilopascal. Okay, show the cycle on a TS diagram with respect to the saturation lines. So as you can see here, that is the TS diagram, okay, and the red lines, this dome is the saturation lines, okay. That is the TS diagram for the actual Rankine cycle. And determine the quality of the steam at the turbine exit. Turbine exit, we said the turbine is between 3 and 4. So the turbine exit is at state 4. Okay, the turbine exit is at state 4. So the quality at state 4. So we need to find at part A X4, and X4, it is the X4 actual, the quality for the actual cycle, okay, because we have actual cycle in this question, isentropic efficiency is given, okay. In part B, we need to find the thermal efficiency for the cycle, and is the actual thermal efficiency, okay. And in part C, the mass flow rate, okay. Of course, it is the actual mass flow rate, m dot, of the steam, okay. So how can we find X4A? So let's see, in our equation sheet we have that X4A is equal to H4A minus HF over HFG. Why especially H يعني. Why not other properties? Because we have the equations for the isentropic efficiency, which is like this. The efficiency of the isentropic efficiency of the bond is the work of the isentropic or the ideal compression process for the bond over the work for the actual bond. Okay. We have the isentropic efficiency. It is given, and H2S can be calculated like the ideal Rankine cycle. Okay, H1 also at V1 equal to Vf and H1 equal to Hf like the previous video. The remaining is H2A. Okay, and here also for the turbine we have the work turbine out over the work the actual work, because that is why we have A here, over the isentropic or the ideal work for the ideal Rankine cycle. And we are given this one. I can calculate the work turbine, the ideal one, like for the ideal cycle. I can calculate H4S like the previous procedure in the previous video. H4 from here. We didn't put S as the subscript S, but here when we have a actual cycle, we will put S to differentiate the ideal cycle enthalpies from the actual Rankine enthalpies. Okay, as you can see, H1 and H3 are the same. That is why they are in the same color. Okay, for both actual and actual and ideal Rankine cycle. Okay, so for the quality, I put X4 equal to H4A minus HF over HFG. HF and HFG can be found easily from the thermodynamics tables, but H4A I can find it using the isentropic efficiency of the turbine, because it is given, and from the previous procedure and what we learned in the previous video, I can find H4S and H3. So then I can calculate H4A from this equation. Okay, that is why we use this property, or the enthalpy, to calculate the quality. Okay, so we need to find X4A, and in order to find X4A, we will use the actual enthalpy, and to use the actual enthalpy, I can find it from this equation, and this equation need to find first what NT or the eta T, the isentropic expansion for the turbine, is given. So I need to find H4S and H3. So I need also to find, before H4S, is to find H4S and H3 in order to use the isentropic efficiency of the turbine to get H4A, and then I can use the equation, this equation, okay, to calculate X4A. Okay, so until now, half of the enthalpies for the ideal Rankine cycle, which is H3 and H4S, we must calculate them before we go to the actual enthalpy. Okay, what about the thermal efficiency? And we know that when he asks for the thermal efficiency, we must get or to calculate all of the enthalpies. Okay, the equation for the enthalpy for the thermal efficiency is this one: 1 minus H4 minus H1 over H3 minus H2. Okay, and here it is actual cycle. Okay, so H4 will be H4A and H2 will be H2A. H1 and H3, we said they are the same for ideal and actual Rankine cycle. As you can see, here it is 1, here it is 3. There is no difference. It is the beginning of the compression process and the expansion process. So it doesn't matter if you go like this for ideal or actual. That is the starting state for you for 1 and 2 and 3. So it doesn't matter if it is ideal or actual Rankine cycle. So 1 and 3 are the same. Okay. So I need to put H4A here and H2A here. And I wrote this one: if the cycle is actual, then use the enthalpies with the letter A subscript. So as you can see here in the equation sheet, we have A subscript, the letter A. So with the actual cycle, use everything or calculate everything with the enthalpy for the actual, the H4A and H2A. So I need also to find what the efficiency in part B, which is 1 minus H4A minus H1 over H3 minus H2A. Okay, so I need to find H2A. Okay, I know that H3 can be found easily. This is like the ideal Rankine cycle. H1 also. H4A will get it from here. and in order to get it, we will calculate H4S and H3. So what about H2A? In order to find H2A, we will use this equation, okay? And this equation, the only difference between it and between the previous equation for H2S, that we divided by the isentropic efficiency for the pump, okay? So that's what we did here. So we can get the actual pump in. The actual work pump in is equal to V1 P2 minus P1 over the isentropic efficiency of the pump. We get it from here that because it is, if I want the actual pump, it will be WS pump in over the isentropic efficiency for the pump. So H2S, the ideal one over this one, will give you the actual pump. And we usually use V1 P2 minus P1. Okay, then you can find the actual enthalpy from here, H2A. And I didn't need to find or to calculate H2S, يعني خلاص, directly we will use this equation to find H2A. So what else? For the mass flow rate, we will use this equation. We talked about this equation before, that it is given in the question that W net power is 210 times 10 to the power 3 kilowatt, okay? So if I have work net output, I can get the mass flow rate. As you can see, kilogram per second, kilogram will go or cancel with the other kilogram, and will give you kilogram per second. Kilojoule will cancel with kilojoule, and will give you kilogram per second. The work net output can be calculated from here. You need to find the work turbine out or the work pump in. Of course, they are the actual turbine out and the actual pump in. Also, this one will be Q in actual, Q out actual, Q net actual, the work net out actual. So everything should be calculated in actual. So you can get the mass flow rate for the actual cycle, okay? Of course, H3 will be the same, H4A, H2A, H2A, H4A. So you only change 4 and 2, H4 and H2. Okay. We will calculate everything. Okay. we will calculate the work net output using the both equations. Okay. Or maybe for time we'll solve with this one only. Okay. In the next question we will solve with both, so we can get see that we can use any one of them. So for the mass flow rate, it will be m dot will equal w dot net given the question over w net actual. So as the ideal Rankine cycle, we need to find all enthalpies for the actual cycle. So let's start with H1. H1 is the same for ideal or actual Rankine cycle. Here I am given the pressures, so I will use the blue one, and it is steam. Given the working fluid is a steam steam inside the power plant. Okay, so let's find V1 and H1 from table A5 under the pressure P1 equal to P4. Okay. So we will write that at P1 equal to P4, which is equal to 10 kilopascal, the condenser pressure, we will calculate V1 equal to Vf at this pressure, 10 kilopascal, and also H1 will equal to Hf at this pressure. Okay, so let's go to the table. I didn't open the table. Okay. Table A5, the pressure table. Okay, we need to find at 10 kilopascal. At 10 kilopascal, we want to calculate V1, which is equal to Vf, and H1, which is equal to Hf. So H1 equal to Hf and equal to 191.81 kilojoule per kilogram, and V1 equal to Vf and equal to 0.001010 meter cubed per kilogram. And then I can go and calculate the work pump in, because now I have the specific volume, the actual work pump in. will equal to V1 B2 minus B1, which is the ideal work pump in, but I will divide the ideal work by the isentropic efficiency of the pump to get the actual work for the pump. So it is 0.001010 times 10,000 kilopascal minus 10 over the isentropic efficiency 0.85, and this will give you that the work pump, the actual work pump in is equal to 11.87 kilojoule per kilogram. And now I can find H2A will equal to H1 plus V1 B2 minus B1 over the isentropic efficiency of the pump. This term is what is the work pump in, and H1 we got it from the table, which is equal to HF. Okay, so H1 is 191.81, and the work pump in is 11.87, and this will give you that H2A is equal to 203.68 kilojoule per kilogram. Now we found H2A. We need to find H3 and H4S in order to find H4A using the isentropic efficiency equation for the turbine, and then we can get X4A. So for H3, it doesn't matter if it is ideal or actual, the same procedure. Okay, we have the pressure given in the question, so we'll use the blue one. Okay, nothing is mentioned about saturated vapor, okay, or the quality at state 3 or nothing, so we'll ignore this one, and we will check if it is superheated, state 3 is superheated or not. Okay, I am given the question T3 and the pressure at state 3, so then T3 must be given, okay, beside the value of the pressure. Okay, that's what we have in the question. So let's go and check, and we check from table, the pressure table, table A5. Okay, from table A5 to check. Okay, so we'll go to table A5. The pressure at state 3 is 10,000 kilopascal. Okay, at this one, and we will compare our temperature T3 with the saturation temperature, and as you can see, my temperature T3 is 500 degrees Celsius, and that saturation temperature is less than my temperature, the T3. So we are in the superheated region. Okay, so it is a superheated state. So at B2 equal to B3 equal to 10,000 kilopascal, T3 is higher than Tsat, the saturation temperature, 500 degrees Celsius is higher than 311 degrees Celsius, so it is a superheated state. Okay, so I will go to table A6, the superheated table for the steam. So let's go to that superheated table, table A6. 10,000 kilopascal means 10 megapascal. Okay, divide by 1,000. Okay, so 10 megapascal with 500 degrees Celsius. I want to find what? Usually for the turbine we said we usually find S and H, right? Why S? Yani, okay, this is an actual cycle. Okay, why you are finding S? Okay, S will equal to S4 if it is only isentropic. Okay, actually yes. Okay, we need to find it is actual cycle, but first in order to find H4A I need to find what? H3 H4S, because this equation is the same like the equation here. Okay, but this one, but we arrange it to make H4A on only one side alone, yani. Okay, so this equation contain H4S, and in order to find H4S I need to find first X4S, and X4S contain S4S which is equal to S3. So يعني usually to calculate everything for the actual cycle, you need to solve for the ideal cycle first. Okay, so that is why I need S3 also to say that S3 is equal to S4S, and go to find X4S, and from X4S I will know in which one of them I will choose from these three cases. Okay, then I calculate H4S, and after I calculate H4S I can now calculate H4A, so I can get the quality. So that is why I need also S3 with H3. Okay, so under 10 megapascal, 500 degrees Celsius, I'll take these two numbers for H and entropy, specific entropy. Okay, so H3 will equal to 3375.1 kilojoule per kilogram. S3 is equal to 6.5995 kilojoule per kilogram Kelvin, and this one is equal to S4S, the ideal specific entropy at state 4. Okay, so now I can use this entropy to calculate, as we said, X4S, which is equal to S4S minus SF over SFG. Okay, so X4S equal to S4S minus SF over SFG at which pressure? It is X4, so pressure P4 equal to P1, the condenser pressure, 10 kilopascal. Okay, to calculate to find SF and SFG, so I will go to table A5, the pressure table. Okay, at 10 kilopascal, and take these two numbers for SF and SFG. Okay, SFG is SG is this one minus SF. Okay, يعني as you like, do whatever you want. Okay, so X4S is equal to 6.5995, this number. Okay, minus SF from the table is 0.6492 over SFG 7.4996, and this will give you 0.7934, the quality at state for the ideal Rankine cycle. Okay, and now I can find H4S because the quality is less than 1. Okay, so we are in this case at less than 1, so I will use this equation to find H4S, and then I will use the isentropic efficiency turbine equation, which we arrange it to be like this to calculate H4A. So then I can find the quality. Okay, so let's find H4S. So H4S is equal to HF plus X4S HFG, and this will give you that HF, which is equal to H1 here because we don't have subcooling at state 1, 191.81 plus 0.7934, and HFG, of course I am getting all of this at which pressure? The same pressure, B1 equal to B4 equal to 10 kilopascal. So you find HF and HFG from the table here also. HF, this one, 1918.81, and HFG 2392.1. Okay, so HFG is 2392.1, and this will give you that H4S is equal to 2089.7 kilojoule per kilogram. Now I can find the enthalpy, the actual enthalpy H4A, using the isentropic efficiency for the turbine equation, H3 minus the isentropic efficiency of the turbine times H3 minus H4S. Okay, this will give us that H4A. H3, we calculate H3 to be 3375.1 minus 0.85 given in the question. H3 3375.1. H4S is this number, 2089.7, and this will give you that H4A is equal to 2282.51, and now I can find X4A. X4A is equal to H4A minus HF. Okay, because I cannot find other properties for the actual properties as state 4 except the enthalpy. We have a relation with the enthalpies for the actual and ideal using the isentropic efficiency for the turbine and also for the pump. Okay, so that is why we use enthalpies HFG. This one also will be at which pressure P1 equal to P4 equal to 10 kilopascal. So no need to go again to the table because we are calculating HF and HFG at the same pressure. That's what we did here for this one, for this equation. Okay, and HF, HFG, this one, these numbers 191.81 and 2392.1 are these also numbers, the same numbers, at the same pressure. Okay, so H4A is 2282.51 minus HF 191.81 over 2392.1, and this will give you that the quality is 0.874. Okay, now we finished part A. The second part was the thermal efficiency, the actual thermal efficiency. Okay, so the actual thermal efficiency is equal to 1 minus H4A minus H1 over H3 minus H2A, and this will give you that the thermal efficiency, the actual thermal efficiency, is 1 minus 2282.51 minus 191.81 over H3 3375.1 minus 203.68, and this will give you that thermal efficiency is equal to 0.341 and equal to 34.1%. For the final part, part C, we need to find the mass flow rate, W dot net over W net, the actual one. Okay, so the actual one, W net A, is equal to the work turbine out minus the work pump in. Okay, and we said it is actual cycle, use the actual enthalpies H4A and H2A. H1 and H3 are the same for the ideal and actual cycles. Okay, so the work turbine, the actual one, is equal to H3 minus H4A, and this will give you 3375.1 minus 2282.51, and the answer will be 1092.59 kilojoule per kilogram. For the work pump, you calculate work pump in at the beginning. So W net A, the actual work net in kilojoule per kilogram, is equal to work turbine out, the actual one, minus work pump, the actual one. Okay, and this will give you that the value is okay, let's substitute 1092.59 minus 11.87, and this will give me 1080.72 kilojoule per this point here, kilojoule per kilogram. Okay, so the mass flow rate m dot is equal to 210 times 10 to the power 3 W dot net. Okay, over the W net actual that we calculated this number. Okay, 1080.72. This will give me 194.3 kilogram per second. Okay, so we finished question, the first question. The second question came in a midterm exam before. Okay, this question 1022. We have a simple Rankine cycle uses water, so we have also water. So table A4 to A6. The R13RA is 10 A11 to A13. Okay, as the working fluid, the boiler operates at 6,000 kilopascal. So boiler pressure is what? Boiler is from 2 to 3, right? Okay, boiler from 2 to 3. So B2 equal to B3 equal to the boiler pressure. Okay, B2 equal to B3 and equal to 6,000 kilopascal. And the condenser at 50 kilopascal, the condenser pressure is P1 equal to P4 equal to 50 kilopascal. At the entrance to the turbine, so at state 3, turbine is here at state 3, okay, state 3. At the entrance to the turbine, the temperature is 450 degrees Celsius. So T3 is equal to 450 degrees Celsius. Okay, the isentropic efficiency of the turbine, so eta T, this one, is 0.94%. Okay, pressure and pump losses are negligible. Okay, and that in the whole book we neglect in this chapter the pressure and pump losses. Okay, and also we neglect the friction in the boiler and the condenser. So we only care we are looking for the irreversibilities in the actual cycle in only pumped in the if it is not isentropic compression or expansion in the pump and the turbine. That is the only thing that we are looking for. Okay, there is other things that we neglect. And the water leveling in the condenser is subcooled. Okay. The water leveling in the condenser is subcooled by 6.3 degrees Celsius. What is the meaning of this sentence? We will see. Let's keep it to the end. Okay, the boiler is sized for a mass flow rate of 20 kilogram per second. Okay, so the boiler is sized for a mass flow rate. So the mass flow rate m dot is equal to 20 kilogram per second, and this closed cycle. So this m dot is during the whole cycle. Okay, and the boiler is sized for a mass flow rate of 10 kilogram per second. Determine the rate at which heat is added. Okay, so the rate means power dot. Okay, so it is Q dot. Added means in the boiler. Okay, then okay, the rate, the power required to operate the pumps. Okay, so W dot, because it is power, so W dot N. And he didn't mention anything about isentropic efficiency for the pump, صح? Okay, so means it is not actual. It is not actual work for the pump. It is ideal work. Okay, and even Q dot N. Q dot N is what? Q dot N. Q dot N means it is m dot times Qn. Okay, m dot times Qn. Okay, so as you can see, m dot times Qn is H3 minus H2, right? And he didn't mention anything about the isentropic efficiency for the pump, and that means that it is equal to 100%. Okay, means it is equal, خلاص, is equal to 100%, means this term is equal to this term. H1 is the same, so H2S is equal to H2A. There is no already actual cycle for or this line. This line is cancelled. Okay, there is no A already. So we have isentropic compression in the pump. Okay, so we only have H2S and in this question. Okay, in the previous question it was given that we have the isentropic efficiency for the pump and turbine. Here we only have for the turbine. So the turbine is the only actual device here, but the pump is an ideal device in this question. Okay, so that is a point that you must care about. Okay, that not if it is okay, it is mentioned as isentropic efficiency. That doesn't mean that the whole cycle, the whole devices are actual. Okay, here only he mentioned for the turbine, so it is 0.94, and this one will be QNS, the ideal heat added, ideal rate heat added to the cycle. Okay, because H2A, we don't have H2A, it's only H2S. Okay, that's why. So Qn.S is equal to m dot, okay, of course, the mass flow rate times Qn the ideal one, okay, for the ideal cycle, and it is equal to m dot h3 minus h2s, okay. And work in bump s, we will not use this equation, okay. This equation for what? For the actual. Actual means that we divide by the isentropic efficiency of the bump, and this isentropic efficiency of the bump is what? Is 1, okay. خلاص يعني 100% means it is 1, يعني 100 over 100, like 0.94, it was 94% over 100, okay. So it is 1. So you use this equation, only this equation without the isentropic efficiency of the bump. So the W dot N bump is ideal, okay, and it's equal to V1 P2 minus P1, okay. The third thing is what? The net power produced by the cycle, okay. And so it is W dot net, the power produced by the whole cycle class. W dot net is not for the turbine, not for the pump, it's the net one, okay. And it is actual. Why actual? Because it will be W dot turbine out, which is actual because we have isentropic efficiency for the turbine, minus the work dot n for the pump. But the pump, okay, it is ideal work, it is not actual, but the whole answer will be actual because we have a turbine, a work turbine actual here, because it is given as an isentropic efficiency for the turbine. And the thermal efficiency, and it will be also actual because we have H4A. Why? Because that is the equation for the thermal efficiency, and here we will have H4A. This one will be H2S, but here H4A is the problem because we have the isentropic efficiency for the turbine given, and I want to calculate H4S like the previous question, and also calculate H3. Then I can get and then find the H4A. So that is why it is the thermal efficiency is actual, okay. And here for this question, when he says the boiler is sized for a mass flow rate, means he made the mass flow rate as fixed for both, for ideal and actual Rankine cycle, yani, okay. So yani, just assume that mass rate is mass rate, okay, and this one is multiplied by m dot, okay. So it is yani, because here it is m dot, okay, and when I want to calculate the turbine out, I will multiply m dot times the turbine out with the small w, okay. I use it for the actual, I use it for the ideal, so the mass rate is fixed for both cycles. That is an assumption you'll assume, okay. Now returning back to this sentence, that the water leveling in the condenser is subcooled. Okay, what is the water level is subcooled by 6.3? Means he is talking about the water level in the condenser, the temperature at the condenser is subcooled by 6.3. So if we draw the cycle, if we draw the cycle, okay, for the thermal efficiency class, we will write the equation at the end, okay. If we draw the cycle on the TS diagram, okay, here we have at stage 3 the turbine inlet, okay, and it is actual, right? Okay, so it is actual, it be like this. So this one is what is 4A, state 4A. But for the ideal cycle, we will go like this. From 3, we'll go in a straight line. Nice straight line. Okay, here, this one is 4S. Okay, the ideal isentropic expansion is S3 is equal to S4S. Okay, but S3 is not equal to S4A. And then we will go to what? Usually we go to the saturated liquid line at state 1, okay, and then we go to 2 and continue to 3. But here he said this sentence that the water level in the condenser is subcooled by 6.3. So the water level temperature, this is the water level temperature here. This one is Tsat, okay. Okay. This Tsat, the saturation temperature at this pressure, okay, This pressure is given in the question. Yes, it is 50 kilopascal. So we can get that value for the saturation temperature from the table. 50 kilopascal is subcooled. The meaning of subcooled mean this state 1 is not now here. Okay, so we'll remove it from here. Okay, and it will not be in this place. Okay, it will be after subcooling. So we will have this pressure line. Okay, this pressure line. The pressure line in the TS diagram is drawn like this, right? Okay, so this pressure line is the 50 kilopascal, all this line. So if it is here the pressure for the condenser, so it is also the same here, 50 kilopascal, here 50 kilopascal. When we say subcooling, means we go down this saturation temperature by a small value, okay, which is equal in the question given 6.3 degrees Celsius. 6.3 degrees Celsius. Here is Tsat, okay, and then that is meaning that we move down. Okay, so let's draw state 1 to be here, for example. This one is number 1. So here is T1. So the difference between the saturation temperature or the temperature for the water level for the condenser is subcooled, so means it goes in the subcooled region here. Okay, and you will follow the same line for the 50 kilopascal, okay, by 6.3 degrees Celsius. Okay, so as you can see, there is a difference between Tsat and state 1. So Tsat at the pressure 50 kilopascal minus T1 will give you 6.3 degrees Celsius. So in order to find T1 is equal to Tsat, because we need T1. Because if I don't have T1, okay, I cannot find the enthalpy for state 1. Okay, you already have the pressure P1. Why not using P1 to calculate H1? Okay, like from this equation, okay, H1 equal to HF, and this what we did when it was saturated liquid. Okay, when it is saturated liquid or saturated vapor or mixture, it will be on the same line, this same line, right? Okay, means the pressure and temperature is dependent on each other. Okay, يعني the Psat will have Tsat directly. B23 B14 here is equal to Psat, okay, at the temperature here 1 and or 4 or any temperature, this line, the isothermal line. Okay, but the problem that when I move down, okay, now, okay, the pressure and temperature is independent. Okay, they do not depend on each other. So if I calculated state 1, which is subcooled in this question, using the pressure, I will get wrong number. Okay, the same thing is for the superheating. Okay, the superheating, the pressure and temperature is independent. Okay, if it that is why in these lines here I didn't find anything about the temperature, because if the state 3 if state 3, this one is superheated like this, okay, you will not see, you cannot find it as the saturation temperature. The saturation temperature or this temperature, okay, will be, okay, if it is state 3 is here subcooled, okay, it is not on the same line for the pressure. Okay, the pressure is this one. Okay, so you will follow the pressure. You cannot say that I will go like this in the same line and this will be the 0.3. No, you are following always the pressure line. So state 3 will follow the pressure line and will be right here. Okay, and here you don't have the temperature. Okay, if it is you need to use both of them, temperature and pressure. And when you go to table A6, the superheated table, you will use both of them. You will go under a certain pressure. That is why in thermodynamics table, in table A6, we have the table is divided with different pressure. Okay, the same thing for the subcooled. When we go subcooling like this, so T1 will equal Tsat minus 6.3 degrees Celsius. Tsat can be calculated from the table at 50 kilopascal. Then I will go up in the pump, okay, to state 2, and then I will go like this, and then I will have superheating. And as you can see, subcooling is one of the things that will increase the thermal efficiency. Okay, it is not mentioned in the slides, but it is one of the things that increases thermal efficiency, because you will increase the area. Okay, as you can see, if it was at state 1 here, okay, if it was at state 1 here at the saturated liquid, you will go directly to state 2 like this, and then you will go up to this point. Okay, as you can see, you lost a lot if you didn't do the subcooling. The subcooling will increase the area for you in this region. You cannot find it if you started with the saturated liquid. That is why they did subcooling in this question, and it is a good thing to increase the thermal efficiency for the cycle. Okay, so by this we can calculate T1. So if I go for the pressure, 10 kilopascal, for the pressure 50 kilopascal, sorry, 50 kilopascal, this one. Okay, the saturation temperature is 81.32. So this one, Tsat is 81.32 minus 6.3 will give you 75.02 degrees Celsius. And this is T1. So now you are given T1, or you calculated T1, you will use T1 to find HF, okay, and VF, which is equal to H1 and V1. Why HF? Because it is a subcooling, okay, subcooled state. State 1 is a subcooled state. Okay, state 1, meaning that it's subcooled. We approximate the values to be equal to HF, and the values of the properties equal to the saturated liquid properties or values. Okay, and this is approximation. Usually we have another term, VB sat minus B1. Okay, but this term is very small, so we cancel it and we approximate that H1 is equal to HF and V1 equal to VF. But where? Not from the pressure table. Liquid or subcooled is a function of temperature. Okay, so you use the temperature table. So at which value? At 75.02. So you go to table A4 for the temperature. Okay, 75.02. you will not find it here. Okay, do not do interpolation خلاص, يعني assume 75 يعني 0.2, it doesn't matter. Okay, so this one is 75 degrees Celsius. So at 75 degrees Celsius, and this one also at 75 degrees Celsius. Okay. Okay. So now let's find HF. Okay. Let's find HF and VF. So from the table A4, under 75 degrees Celsius, I'll find V1, which is equal to this value, and H1 equal to this value, HF. So this one will give me 314.03 kilojoule per kilogram, and V1 equal to VF will equal 0.001026 meter cubed per kilogram. And now I can find, and it is mentioned the question thermal efficiency, means we'll find everything. So let's find everything, all enthalpies in actual, ideal. Okay, so I found H1 and V1. Let's find the work pump in, and this, we said it is ideal, right? Because we are not given the isentropic efficiency of the pump. So it is equal to V1 B2 minus B1 directly. Okay, V1 is what? 0.001026. B2 given in the question and B1 given in the question also. So 6000 minus 50 kilopascal. Okay, and this will give that the work pump in is 6.1 kilojoule per kilogram. Okay, now let's find H2 S, not A, because it is isentropic expansion. Okay, that is the representation or the TS diagram for the isentropic compression. Sorry, isentropic compression. inside the pump. It is not actual process, okay? It is ideal process, internally reversible process, okay? So H2S is equal to H1 plus V1 P2 minus P1. P2 minus P1 is the work pump N. So H1 is 314.03 plus 6.1 the work pump N, and this will give that H2S is equal to 320.13 kilojoule per kilogram. And now I want to find HS, H3. H3, nothing is mentioned about it is saturated vapor, so I will ignore this line. Okay, so I will need to check if it is superheated or not. Okay, so let's check using table A5 with the pressure given in the question, and T3 is given in the question. T3 is given in the question. Okay, nice. So let's check from table A5. I will go to the table A5. The pressure P3 equal to P2 because I want to find what H3. So I will use pressure P3. The boiler pressure 6,000 kilopascal. So here my temperature T3 is 450 degrees Celsius. It's higher than the saturation temperature, so we are in a superheated region. So it is a superheated state. Okay, so I would say that at B2 equal to B3, 6000 kilopascal, T3 is higher than saturation temperature, so 450 degrees Celsius is higher than 275.59 degrees Celsius, and it is a superheated state. Okay, I will go to table A6, the superheating table, under also the same pressure and temperature. So 6,000 kilopascal يعني 6 megapascal. 6 megapascal is here with a temperature 450 degrees Celsius, and we said we want to find what? Both H3 and S3, okay? Because you need to find H4S before you find H4A. Usually you find everything for the ideal before you calculate anything you want for the actual. And we need S3 because it is equal to S4S. So I need to get H3 and S3. So H3 is equal to 3302.9, okay, and S is 6.7219. So kilojoule per kilogram, and S3 is 6.7219 kilojoule per kilogram Kelvin. And this one is equal to S4S, okay? S4S, the blue line, not the red line, line, okay? So X4S, let's find the X4S. Why I need to find X4S? Because X4S will let me know how can I find H4S. Is it using this equation, okay, or it is saturated vapor? Rarely will happen, and if it is superheated, okay. So that's why I need to find X4S, and that's why we got S3 from the table. So we can say S3 is equal to S4S in the isentropic expansion process and calculate X4S. Then I can check after I calculate H4S, I can use this equation to calculate H4A, and after this I already found everything, so I can calculate the thermal efficiency, okay, and I can calculate work turbine actual, which is this from this equation. Either you choose or find this equation, or after directly you find H4S, you use this equation with the isentropic efficiency of the turbine, okay. But خلاص يعني we will find H4A, and this will use this equation because already we need to find the thermal efficiency, which contains H4A. So let's find X4S. X4S is equal to S4S minus SF over SFG, okay, at pressure P4 equal to P1, state 4, 50 kilopascal. S for S is this value 6.7219. SF and SFG from the table at table A5, 50 kilopascal. So at this pressure, we will calculate or get SF and SFG. Minus SF 1.0912, okay, over SFG 6.5019, and this will give me that X for S is 0.866, okay. And now this one is less than 1, so I will use this equation to find H for S. H for S equal to HF plus X for S HFG. HF, now it will not equal H1 as usual, and we want to check if our solution is right or no, because H1 was subcooled, okay, and HF that you are finding now is at this point, okay, but H1 is here, so there is difference, okay. So when you have subcooling, you will not have HF equal to H1 for at the pressure, okay. As we said, we used what to calculate H1? We used the T1 that we calculated here, okay. T1, this value 75 degrees Celsius. If you use the pressure, you will get HF, which is here, okay. So that is why. HF is 340.54. X4, we calculate X4 0.866, and HFG from the table, everything from the table, okay, at the pressure 50 kilopascal, HF, this one, and HFG, this one, okay, times HFG 2304.7, and this will give me that H for S is equal to 2336.41 kilojoule per kilogram. Now I found H for S. I can use the isentropic efficiency for the turbine equation to calculate H for A. Okay. So H for A is equal to H3 minus the isentropic efficiency for the turbine times H3 minus H4S, okay. So H4A will equal to 3302.9 minus the isentropic efficiency of the turbine 0.94 times 3302.9 minus H4S to 336.41. And now we can find H4A. H4A is equal to 2394.4 kilojoule per kilogram. And now we can go to the second requirement, which is Q.N, the rate of heat addition, okay, which is equal to m dot H3 minus H2S, okay. We calculate H2S. Yes, it is okay. You calculate H2S. Okay, and then we will find what we found the work pump N. We didn't find the work pump N. He needs the power. Okay, so we need to multiply with the mass flow rate. Okay. Also, we need to find what the thermal efficiency. I remember. Yes, we need to find also the thermal efficiency. Okay. So let's find Q dot N, which is equal to m dot Qn and equal to m dot H3 minus H2S. So m dot is 20, H3 is 3302.9 minus 320.13, and this will give you Q dot N. Q dot N is 59655.4 kilowatt. Okay, for the work dot pump N, it is ideal, both of them ideal. Okay, it's equal to m dot times the small work pump N Okay, m dot is 20, and this we calculated this value to be 6.1, so it will be equal to 122 kilowatt. And now to find the thermal efficiency, let's use the other equation. يعني instead of using this equation H4A, خلاص, let's calculate everything. Okay, let's calculate the work net output. Okay, and calculate work turbine out, pump in, and calculate the work net output from this equation, and let's calculate Q out. Okay, so we can use for the W dot net power, you can use this equation also. يعني do whatever you want. Okay, يعني it doesn't matter. Okay, so let's calculate the work turbine, the dot turbine out, the actual one, because we have the isentropic efficiency for the turbine. It is equal to m dot times the work turbine out, which is the actual. Okay, actual one. So it is m dot times what? H3 minus H4A. Okay, because actual. So m dot is 20, H3 is 3302.9 minus 2394.4. So work the turbine out, the actual one is equal to 18170 kilowatt. Okay, and let's calculate also Q dot out. We will not lose anything. Q dot out actual, but of course يعني in the exam يعني خلاص choose one and continue, يعني will not have the whole time. Q dot out actual is equal to m dot Q out actual 20 times H4A minus H1. Q out also is actual because it contains 4. State 4 is actual state. That's why. Okay. So let's substitute here. 20 times 394.4 minus H1 314.03, and this will give you the answer 41607.4 kilowatt. Okay, as you can see, usually Qn is the highest value. Okay, we have يعني approximately low value for the work pump in compared to the work turbine. So as we said before in the previous video. Okay, let's calculate W dot net actual, work dot turbine actual minus work dot pump ideal, because يعني خلاص there's no isotropic efficiency of the pump, and this will give me 18170 minus 122. The answer will be 18048 kilowatt. Okay, the thermal efficiency will be, the actual thermal efficiency will be W dot net over Q dot N. This one is actual, this one is ideal. Okay, this 18048 over 59655.4, and the final answer will be 0.3025, which is equal to 30.25%. Okay, that is for this video about the actual cycle. We'll have inshallah other videos about Rankine cycle with reheating.